Right, I'm going to answer the question now. How many primitive roots does n, the integer n, have? Remember that a primitive root is a primitive root. A is a primitive root, if a to the power phi of n equals 1, everything modulo n, and no smaller power will do. No smaller power of a is equal to 1. So that's what it is. Well, I need to. It's not entirely straightforward. It's not entirely straightforward. You can show every prime number has a primitive root, but what about composite numbers? Well, let's have a look at this. So I'm going to consider the set a squared, a cubed, a to the 4, blah 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 blah, a to the power phi of n, where a is a primitive root. Primitive root. So NB, we are assuming that n has one, that n has a primitive root. So everything I'm going to say is contingent on being able to find an a which is a primitive root. So this set here is equal to the set x1, x2. Well, let me rephrase it. It's equal to the set x such that nx equals 1 and x is less than or equal to n. So the set of x which is less than or equal to n and relatively prime here to n, this set here is the same set as this set here. These two sets are equal. How do we know that? Well, these guys here are all incongruent. These guys here are all, there's no repeats in there, they're all different. We know that. And there's no repeats here in this set either because they're all different as well. And they're the same number. They're the same, the two sets have got the same cardinality. So they're equal. They're equal. Okay? So, if A is a primitive root, we're always assuming that that the number n has a primitive root. Then any other primitive root is a member of the set. Well, it's a member of this set here, so specifically it's a member of the set a squared, a cubed, blah blah blah, up to a to the power phi of n. Okay? So if a is a primitive root, any other primitive root is going to be part of this set. Of course, there's a itself, but there might be another primitive root in here as well. So which powers, if a to the k is a primitive root, then we know that k and phi of n are relatively prime, because if it wasn't prime, a to the k would not be a primitive root because it would come to 1 with a smaller power than phi of n. So how many k's? How many k's are there with that property? Well, it's just by definition the totient function of the totient function of n. So if n has a root, how many has it got? It's got this number here. Okay, which is quite nice. So let's have a nice example of 9. We know that 9 has got a primitive root in as much as 2 is a primitive root. Primitive root of 9. Well, let's have a look at that. Let's do everything modulo 9 and see what happens. We've got 2, 2 squared, 2 cubed, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8. And I'm asserting that 2 is a primitive root of n. So what I want to do is to make this number applicable, because the proof that I've given you that the number of primitive roots is this relies upon there being at least one, or a, primitive root. So that's 2, that's 4, that's 8, that's 16, which equals 7, of course. Times 2 again is 14, which equals 5, everything being modulo 9. Times 2 is 10, which equals 1. And of course, 5 of 9, of course I was thinking 5 of 9 was 8, but it isn't, it's 9 times 1 minus 1/3 equals 6. And we know that the smallest power of 2 that gets you back to 1 is equal to 6. So the order of 2 equals 6, modulo 9, and 5 of 9 equals 6, therefore 2 is a primitive root. Therefore 2 is a primitive root of 9. So it's got a prime, it's got a root. How many roots? How many primitive roots? Well, it's phi of 9, which equals phi of 5, 9 was 6, wasn't it? So what's phi of 6? Well, it's 6 times 1 minus a half, 1 minus 1/3. 2 times 3 times 1/2 times 2/3, loads of cancelling, equals 2. So there are 2 primitive roots of 9. So some composite numbers have primitive roots. Some composite numbers have primitive roots. I think you can show that all prime numbers have primitive roots. I won't prove it, but you can show this. All primes have primitive roots. It's not an involved theorem, but it's just a bit messy and a bit difficult and not very interesting. And of course, how many? Well, if you assume this, which I won't prove, then we've got phi of p, if p is prime, equals phi of p minus 1 primitive roots. Okay, which is quite nice. Now, you can spend a lot of time mucking about like this, but basically n has primitive roots, and I will not prove this either, because the proof is quite long, if and only if n equals, or actually, yeah, n equals one of these things here. It can either be 2, or 4, or p to the power k, or 2p to the power k, where p is an odd prime. Okay, and if n is of that form there, n has a primitive root. So, for example, 5 cubed equals 125 has a primitive root because it's of this form here, or 2 times 5 cubed has a primitive root. What's that? 250. But a number like 3 times 5 equals 15, no, this has got no primitive roots because it's not in this form here. The proof's messy and difficult, but what I want you to pick up is that some integers have primitive roots and some don't. I guess I should specify k is greater than or equal to 1 here. So if it's a prime or double a prime, it's got primitive roots. Or a prime power, or twice a prime power, or 2 or 4, then it's got primitive roots, otherwise none. Okay, stop there.